Dear students, welcome to this lecture on the relation between the continuous and discrete systems. So, in this lecture we will see the controllability property of the continuous and discrete system and their relations. That is, in many practical problems, a continuous control system of this form x dot t equal to a x plus b u with initial condition x of t naught equal to x naught needs to be converted into a discrete control system, because when we solve a continuous system using a digital computer, then it is required that it has to be discretized and then solved. So, when we discretize a continuous system, then the important properties such as the controllability, observability, stability should not be lost in the equivalent discrete system. So, we will see that under what condition the continuous system and the corresponding discrete system behave in a same manner. So, in this lecture we will consider the controllability properties of these two systems. So, we consider the system 1 and let us take the initial time instant as t naught, and we can write it in the form of k naught into h, where k naught is a suitable integer and h is a small number, positive number. Then we consider the discrete time instances t1, t2, tk etc., where it is given by the increment in each is h, that is t k plus 1 minus t k is always equal to h, the discrete. We consider t k to be equal to k 0 plus k into h, where k is 0, 1, 2, 3 etc., the time instances. Now, we can find the value of the state x of t1, x of t2 etc., at the time instances, discrete time instances. So, x of t1 is given by phi of t1 t0 into x of t0 t naught to t1 of phi of t1 s b u s ds. So, that is nothing but e to the power, because phi of t comma s is equal to e power a t minus s, the for the constant matrix A autonomous system. So, we get e to the power a t1 minus t naught is h into x of t naught plus integral t naught to t1 in the e to the power a t1 minus s b u s ds. So, here we are considering the t naught to t1, s is in between. So, we can write s as t naught plus some theta, where theta is from 0 to h. So, substituting this value of s in the integral, we get the expression x of t1 is e power a h into x of t naught plus integral 0 to h e power a theta b u s ds. So, same way we can also calculate x of t2 as given in this expression. So, if we define the control function u of t as a discrete type of function, u of t k in the interval t k to t k plus 1. So, in this interval we have t naught, t1, t2, tk, tk plus 1. So, we take the u function as a step function type of thing, that is its value u of t in the interval t naught to t1 is u of t naught, and in the interval t1 to t2 is the value u of t1. So, etc. So, we can get the discrete values for the control function u of t, which takes the value only in the left boundary of each interval. So, substituting this u of t step function inside the integral, in the integral here. So, the first integral t naught to t1 u of s is u of t naught. So, that can be taken out of the integral, we get the expression to be like this. Similarly, x of t2 is e to the power a into t2 minus t1 x of t1 plus integral t1 to t2 of this u of s. So, u of s is now u of t1 because it is in the second interval, and s is equal to t1 plus theta, where theta varies from 0 to h, and substituting that we will get the integral like this. So, now if we proceed in the similar way, we get x of tk plus 1 is e power th into x of tk into plus integral 0 to h e power a theta d theta into this. Now, if we use this notation, x of k is x of t suffix k and u of k is u of t suffix k. E is the matrix given here, e to the power a h, and f is the matrix given in this second term, integral 0 to h e power a theta d theta multiplied by the matrix B. So, if this matrix is f, then by substituting this in the equation 4, we get the corresponding discrete system, that is x of k plus 1 is e x of k plus f u of k, k is ranging from k0, k0 plus 1 etc. So, from the continuous system 1, we are getting the discrete system 5 here. So, now can we use this discrete system for all purpose, that is the controllability, observability, stability of system 1, can we apply it to the system 5 as it is. So, that is what the question is. So, we will see here the following theorems that in some cases the controllability is lost for the discrete system. If the continuous system is controllable, always there is no guarantee that the discrete system is also controllable. So, we have to be careful about the selecting the discrete points, so that the controllability property is preserved between the continuous system and the discrete systems. If we consider the matrix U is B, A B, A square B etc. a power n minus 1 B, and if the rank is equal to n if and only if the rows of the matrix e power a t into B are linearly independent for all t greater than 0. Similarly, the rank of U is equal to n if and only if the rows of the matrix Z I minus A inverse into B are linearly independent for Z belonging to the complex plane and Z is non-zero. So, any one of these conditions are now equivalent. The rank of U is equal to n, it is equivalent to the rows of e power a t into B are linearly independent, or that is also equivalent to the rows of Z I minus A inverse into B are linearly independent as given in this theorem. So, we can briefly see one of the proofs. So, if the rank of U is less than n, we can prove that the rows of e power a t into B are linearly dependent, and if the rows of e power a t into B are linearly dependent, then rank of U is less than n. So, this two condition becomes equivalent. Similarly, we can also prove the condition for the first and third, which are equivalent conditions. So, if rank of U is strictly less than n, then there exists a vector alpha belongs to Rn such that alpha dashed into U equal to 0 and alpha is not 0. Non-zero vector alpha will exist, so that this is set. It is a usual property of matrix. So, now if we also prove that to show that the rows of e power a t into b are not linearly independent. Again, if you are able to show that, now we show that alpha dashed into e power a t into b also will be equal to 0 for this same non-zero vector alpha. So, if this condition is satisfied, then it is clear that the rows of e power a t into b are not linearly independent in that case, because there exists a alpha non-zero satisfying this condition. So, we can write it directly, that is we want to show that alpha dashed into this, if you expand it, we will get b plus t into a b plus t square by 2 into a square b plus etc. So, if you want to show, if you show that this is equal to 0 for all t greater than 0, then we say that the rows of this matrix is they are linearly dependent in that case. But that is very obvious, because alpha dashed into u equal to 0, it implies alpha dashed into the matrix u is b a b a square b etc., that is equal to 0. Or separately, if you take the blocks, this implies alpha dashed b is 0, alpha dashed a b is 0 etc., alpha dashed a power n minus 1 b equal to 0. So, then it is also obvious that alpha dash a power n into b, a power n minus 1, n plus 1 into b etc., they also will be equal to 0. So, from the previous step we can see that we can just multiply alpha dashed into b, first term, that is 0, alpha dashed into a into b, that is also equal to 0, where t is a variable here, but alpha dashed into a b is 0, alpha dashed a square b is 0 etc. So, all the terms are equal to 0. So, this implies that alpha dashed into e power a t into b equal to 0 for all t greater than 0. So, this implies that the rows of the matrix e power a t into b are linearly dependent. So, in the similar manner we can show the converse also. If alpha dashed e to the power a t into b is equal to 0 for all t, then if we go in the reverse process we can show that the separately they are all 0, that is alpha dashed into b is 0, alpha dashed into a b is 0 etc. So, that can be shown. With a little bit more effort we can show the converse part of this one. Similarly, we can show that if the rank of u is less than n, then the rows of z I minus a inverse b is also they are linearly dependent. So, the second part is here we can write z I minus a inverse b. So, this can be written as, if you take z outside from the bracket, we get z inverse into I minus z inverse a inverse into b from this one, and if we expand I minus z inverse a power minus 1, we will get I plus z inverse a plus z inverse a whole square etc. infinite series multiplied by b. So, if we multiply it again, we will get z inverse into b, the first term, plus z power minus 2 into ab, plus z power minus 3 into a square b, plus etc. So, we can see that it is similar to this e to the power a t b. Here they are all in terms of t, a function t square by 2 etc. is the variable coming in this equation. Here the variable is z in a slightly different way, but the structure is the same. We have b a b a square b as the coefficient of these variables. So, the same argument, if rank of u is less than n, there exists a alpha dashed such that alpha dashed into u equal to 0. That implies the same thing, alpha dashed of b is 0, alpha dashed of a b is 0 etc. for the non-zero vector alpha. So, if you multiply alpha dashed with this one, so this implies that alpha dashed of z I minus a inverse into b equal to 0, because each term is separately 0. Alpha dashed into b is 0, alpha dashed into a b is 0. This is true for all z not equal to 0. So, we can easily see that the size of the matrix is n cross n, because A is a n cross n matrix and I is n cross n. So, the inverse is also n cross n and B is n cross m. So, the matrix is a n cross m matrix. There will be n rows here and they are all function of, they are not constant rows here because z is a variable. So, there are n rows which are functions of z here. So, we are considering the linearly independence and dependence of functions, the vector functions here. So, it indicates alpha dashed into that matrix equal to 0 for all z implies that the vectors are linearly dependent here. So, the conclusion is if rank of u is strictly less than n, then the rank of z I minus a inverse b is also they are linearly dependent. Similarly, if the rows of z I minus a inverse into b are linearly dependent, then the rank of the matrix U is strictly less than n. That can be also proved here. So, it automatically implies that the rank of U equal to n if and only if these conditions are satisfied in both sides. So, now we can observe that the U matrix rank of U equal to n implies the controllability of the system x dot equal to A x plus B u. So, if the continuous dynamical system is controllable, now we want to see under what condition the corresponding discrete system is also controllable. So, the system continuous system is x dot equal to A x plus B u and the corresponding discrete system is x of k plus 1 equal to E into x of k plus f into u of k, where E is given by this expression as we have seen earlier and f is given by this. A and B are constant matrices. Now, we want to show the controllability of the system 6. 6 is the discrete system. So, if the continuous system is controllable, when the discrete system is also controllable. So, just we have seen in the previous theorem that the system 6 is controllable if and only if the either we have to show that the rank of f E f e square f etc. e power n minus 1 f. So, that should be equal to n. This is the standard condition for the controllability of the autonomous system, but here E is the matrix e to the power a h and f is the matrix given by the previous expression, where f is given by m into b, where m is given by this e to the power a theta into d theta integral 0 to h. So, f is given by m into b. So, in order to prove the controllability of the system 6, we have to show that the rows of the matrix Z I minus E inverse F they are all linearly independent by the previous result. So, now F is given by m into b, where m is given by this. So, we want to prove that the rows of the matrix Z I minus e power a h inverse into m b are linearly independent. Now, we can show that the matrix Z I minus e power a h inverse and m, these are commutative, because m is given by this expression and the matrix Z I minus e power a h, its inverse, as we have seen earlier, if we take z outside this integral, it is I minus z inverse etc. So, its value is I plus z inverse e power a h plus z power minus 2 e power 2 a h plus etc. infinite series, and similarly the matrix M is also made up of the matrix e to the power a type of thing. We can do the integration of this, we will get the similar result. This is so that is also equal to e power a h minus I, is not it? This expression we will get the solution of this one. This matrix into if you observe the matrix M equal to integral 0 to h e power a theta d theta, we can see that the M matrix and Zi minus e to the power a h, they are commuting, because we can see that Zi minus e power a h inverse into 0 to h e power a theta d theta will be obtained by multiplying the terms like e power a h into e power a theta, but they are commutative because it is equal to e power a theta into e power a h. So, in each term e power a into h and e to the power a into theta, or e power 2 into a h e power a theta, these are all always commuting. So, we get finally the commutativity property of this expression. So, in order to prove the controllability of the discrete system, we have to prove that the rows of the matrix Z I minus E inverse into F are linearly independent. So, instead of doing that, if we substitute F equal to M into B and M is taken to the left side of Z I minus e to the power A h. So, we have to only check the linearly independence of the rows of the matrix Z I minus e power A h inverse multiplied by B. So, but M is a non-singular matrix. This one is a non-singular matrix that can be verified, because for any matrix A, e to the power A theta is non-singular, and by after putting the limits we can see we will arrive at a non-singular matrix. So, if M is non-singular, then the rank of M into this matrix is same as the rank of the remaining matrix. So, we have to only see that the rows of Z I minus e to the power A h inverse into B are linearly independent. So, this theorem is useful, this result is useful in deciding the controllability property of the discrete system. So, we will not give the elaborate proof of this expression, because it is quite lengthy and we have to consider the Jordan canonical form and so many other lemmas behind this. So, what we will see is the result, we have to test the linearly independence of the rows of this matrix, which is the equivalent to the controllability of the discrete system. So, using that previous result, we can come to this particular conclusion. The theorem gives that if lambda 1, lambda 2, lambda n are the eigenvalues of the matrix A. So, in the matrix continuous system x dot equal to A x plus B u. So, in this system A is the given matrix. If lambda 1, lambda 2, lambda n are the eigenvalues, then the controllability of the system 1 implies the controllability of the system 2 if the real part of lambda I equal to real part of lambda j for some I and j. So, any two eigenvalues lambda I and lambda j have same real part, then their imaginary part should be like this. That is, imaginary part of lambda I should not be equal to imaginary part of lambda j plus 2 alpha k 2 pi k by h here. Okay. So, the imaginary part of lambda I, so if it is equal, for example 2 pi k by h, then the system, the discrete system is not controllable. Even if the continuous system is controllable, if B, A, B, etc. A power n b has rank n, and if the eigenvalues behave like this, the real parts are same and the imaginary part are like this for k equal to 0 plus or minus 1 etc. So, if k equal to 0, that means imaginary part is also the same, real parts are the same, imaginary parts are the same. So, the eigenvalues are repeated lambda I equal to lambda j, but if they are distinct, lambda I is not equal to lambda j, but the real parts are same and the imaginary parts are like this. For example, for k equal to 1, if you have imaginary part of lambda I is imaginary part of lambda j plus 2 pi by h, where h is the time increment, then the system, the discrete system will not be controllable even though the continuous system is controllable. So, one conclusion is, if the eigenvalues are distinct, completely distinct and real, then the system is the controllability of the continuous system implies the controllability of the discrete system. And if the real parts are the same and imaginary parts are behaving like this in this expression, then the controllability of the continuous system implies that of the discrete system. So, that is the conclusion of this particular theorem. The proof of this theorem is based on the proof of this expression, that is Zi minus e to the power a h inverse into b. Now, we will see for some simple example this particular concept. So, if you assume that the matrix A is given by this lambda 1 is the eigenvalue and lambda 2. So, let us say lambda 1 is not equal to lambda 2 and it is in the Jordan canonical form like this, and the matrix B is a column vector B1, B2, B3. So, in this case the system x dot equal to Ax plus Bu is controllable if we have B is a column vector B1, B2, B3, A into B, that gives lambda 1 B1 plus B2, and second is lambda 1 into B2, then lambda 2 into B3, third row into the column. Now, A square B is the first row into this, we will get lambda 1 square B1 plus 2 lambda 1 B2. Then second row into this column will give 0 lambda 1 square B2. Third row into this will give lambda 2 square into B3. So, this is the U matrix. So, if this we can observe that here, if lambda 1 is not equal to lambda 2, then in all the cases the system, the rank of the matrix is 3 and the system is controllable. So, this implies rank of U equal to 3, that implies controllability. Now, the equivalent discrete system, so that is given by x of k plus 1 equal to E x of k plus f into u of k. So, if we calculate here the matrix E is equal to A into h, where h is the time increment, some small real number. So, if you calculate exponential for this Jordan canonical form, we will get e to the power lambda 1 h, then h into e power lambda 1 h 0, then e power lambda 2 h, and F matrix is given by integral 0 to h of e to the power a theta. So, in the place of h we have theta. So, it is e power lambda 1 of theta and theta into e power lambda 1 theta 0 e power lambda 1 theta into d theta. So, this whole thing is multiplied by B1, B2, B3. So, this matrix is the F matrix here in this problem. So, after evaluating we may get some expression, let us call it as B1 bar, B2 bar, B3 bar after calculating this integral. So, here we will get the condition that this expression, now u bar is nothing but this expression f is in the place of b, the first column, the second column is e into f, e square into f here. So, we can see here in case of lambda 1 equal to lambda. Okay. So, now in the previous theorem we have seen that instead of checking the controllability for E and F matrix, it is sufficient to check the controllability for E matrix and B matrix, because M is commutative with the Zi minus e power Ah inverse matrix. So, we have concluded that it is enough to consider e power Ah and B matrix for the controllability. So, we see here e to the power Ah is given by this, and we need not consider this F matrix as product of this and this. It is enough to consider only the B matrix for the controllability. So, we can check the rank of the matrix e power Ah, e power Ah into B and e power 2Ah into B. That should be equal to 3. If you are able to get this expression, then we say that this discrete system is controllable. Because if you calculate this f as given here and calculate B1 bar, B2 bar, B3 bar, that is one way of checking the controllability of the discrete system. But we have earlier shown the equivalence condition, that it is enough to check with e power Ah and the B matrix itself the controllability. So, we check this one. So, if you calculate this 3, e power Ah is given here and B matrix is given. So, what we will see here is we have B1, B2, B3 and e to the power lambda 1 h into B1 plus h into e power lambda 1 h into B2, that is first element, e power lambda 1 h into B2, second element, and e power lambda 2 into B3. The next is e power 2 lambda 1 h into B1 plus h plus 1 into e to the power lambda 1 h to B2. Okay. So, now we can see that in this expression, if real part of lambda 1 equal to real part of lambda 2 and imaginary part of lambda 1 is imaginary part of lambda 2 plus 2 pi k by h. So, this will imply that e power lambda 1 h will be equal to e to the power lambda 2 into h. That can be easily verified from this expression. So, if e power lambda 1 h and e power lambda 2 h both are same, so that will imply that the second row and third row will become the same here. So, this will imply the rank of this matrix will be 2. So, if you call this matrix as U bar, the rank of U bar is equal to 2 in this case. So, this implies the system is uncontrollable. So, this example illustrates that the condition given in the theorem statement, the imaginary part should be behaving like this. So, that implies the uncontrollability of the discrete system provided the. So, if we select the imaginary part of lambda 1 and imaginary part of lambda 2 in this manner for any integer 0 plus or minus 1 etc., any of this integer satisfies this condition, then we get e to the power lambda 1 h equal to e power lambda 2 h, and substituting the values here in the U bar matrix, we get the second row and third row to be the same, and that implies the rank of U bar is equal to 2. So, that implies the discrete system is uncontrollable. So, we have seen through an example that the controllability of the continuous system need not imply the controllability of the discrete system. So, it is essential to select the discrete points suitably, so that the property of controllability is maintained between the continuous and the discrete system. So, in the next lecture we will consider the observability property and the stability property of the discrete system and the corresponding control continuous control systems. Thank you.